Math 1314, Tyler Junior College, Section 2.2, More on Functions and Their Graphs. In the previous videos, we defined what it meant for a function to be increasing, decreasing, and constant on an open interval of x values. In this video, we're going to define what it means for a function to have a relative maxima or relative minima. I should say relative maximum and relative minimum at a particular point on a graph. And for the record, maximum as a noun is singular, its plural is maxima. The same as bacterium, one, bacteria, plural. Similarly, minimum as a noun is a singular noun. Minima is the plural of minimum. Before we get into the example on the right side of the board, let's partition this. Let's see if we can intuitively define what we mean, rigorously define what we mean by a relative maximum and a relative minimum, by intuitively appealing to the graph. Here we have a generic graph of some function y equals f of x. Where on this graph do you think is a relative maximum? Now, relative means I may not be the highest point on the whole graph, but I'm the highest point on part of the graph. As you move from left to right, this peak represents what's called a relative maximum. Because intuitively, it's not the highest point on the whole graph, there are higher points over here. But relative to this portion of the graph, it is. So where do you think the relative minimum is? It's in the valley over here. Relative minimum. And again, it's not the lowest point on the whole graph. There are lower points implied over here. But relative to this part of the graph, it is the lowest point. But can we come up with a more rigorous definition? Well, when we say maximum and minimum, what are we referring to in terms of coordinates, the x or the y? Would you say at this point on this portion of the graph, that's the largest x? You know what, let's just do this. Between my hands at this peak, would you say at that point that's the largest x or the largest y? It's the largest y. So when we say maximum and minimum as adjectives, we're referring to the y values in that portion of the graph. But what do we mean by that portion of the graph? Well, let's see if we can come up with a rigorous definition. A function f of x has a relative maximum at x equals c if we're saying this point is a maximum at x equals c, that means that the x coordinate down here on the x-axis is c. So what do I mean by being the highest point on that portion of the graph? Well, we kind of have to put on blinders and only focus on a portion of the graph. So we're going to cut off a portion of the graph from A to B. Now, it's important to decide whether or not the interval over which we're looking is open or closed. The definition stipulates that it's open. There's a problem if it's closed. I can show you what that problem is in a minute. But let's say that let's just say it. Your relative maximum, if there's an open interval containing your x, such that you're the highest y value on that open interval. In other words, this open interval on the x-axis is saying, look, let's just look at the portion of the graph between the two dotted blue lines. So a function has a relative maximum at x equals c if there exists an open interval from A to B containing C such that, what are we saying about the y value at this point? That it's the highest y value on the entire interval. So to say that in terms of functions, the y value is the output. So we'll say that f of c, the output here, is greater than f of x for every x not equal to c in the interval. In other words, if you pick any other number in the interval besides the place we claim to have the highest value, like right here, and calculate its y value, it's not going to be as high as this guy's y value. He has the highest y value in this interval. And notice that we don't have to check every interval, there just has to exist an interval. It can be a big one or even a really small interval, because we may have a real tight curve and then zip back up. In other words, we could have a graph that does this. This little peak right there is considered a relative maximum, because if we zoomed in close enough, it would look like that, and there would be an interval over which it has the highest y value. So how can we define a relative minimum? Well, pretty much the exact same way. But when we say minimum, minimum what? Minimum y value, or relative to the function, minimum output. So the discussion over here is the same. I know I've already said C over here and A and B, but let's pretend that's not over there because I'm about to use them again. A function f of x has a relative minimum at x equals c. So we'll go over to c on the x-axis. If there's an interval, so we'll say a to b, such that the lowest y value is at c. So pretty much the same definition, we just have to turn this symbol around. If there exists an open interval, and again, we'll call it A to B because I want to make the definitions as similar as possible, except where necessary. There exists an open interval A to B containing C. So C is bigger than A, but less than B. Such that and now the stipulation is the output at C, so f of C, is not greater than all of them, but less than all of them, is less than f of x for every, if I can spell, for every x not equal to C in the interval. So in other words, if you pick any other number in the interval besides C, so let's pick this one, we'll call it x, then its output is going to be greater than yours. Why? Because you're the relative minimum. You're the lowest guy in the portion of the graph. Now, if all of this messed with your head and makes you think, okay, I quit, don't, for two reasons. Number one, notations like this take getting used to. And two, notations like this are more important in calculus. So if you're not headed towards calculus, this is just a temporary inconvenience. How do you answer the question, where is there a relative maximum, what is it, or the same thing for a minimum? You can answer those based on intuition. For example, let's consider this graph, which was the same one we used in the previous video to do an example of increasing, decreasing, and constant. First off, let's identify where the maximum and minimum points are. I think it's pretty obvious where a maximum is. A relative maximum is up here. So we're going to say that 3, 9 is a relative maximum. It just seems like it is. It's a high point. See? It's a high point. Are there any relative minima, low points? Well, there's a low point here, so this looks like a relative minimum. But what about this corner? Would you say it's a maximum? I wouldn't say it's a minimum. If anything, it's a maximum if it's that. Believe it or not, it isn't. And I know you might be thinking, but isn't this the high point right here? Yes, but, and this is where the rigorous definition gets to decide, are you a maximum or a minimum? You're a maximum if, when I go to your x-coordinate on the x-axis, I can open up an open interval around you so that you are the highest point in that interval. No one is higher than you. Greater than, not greater than or equal to. Are there points in this interval where the y-coordinates are the same or greater than this one? Yeah, all of these. So in other words, if you call him a maximum, you have to call everybody a maximum. But everybody has to be lower than me in an interval if I am a maximum. So no, he's not a maximum. He's higher than the guys on his right, but he's not higher than the guys on his left. So he doesn't get to be a maximum. That's why this says greater than, as opposed to greater than or equal to. Because if it said greater than or equal to, then we could say this point is a maximum, which it clearly isn't. It's not higher than the points around him. But its y value is greater than or equal to all the y values around him. So he's not a maximum, he's not a minimum, he's not anything. And by the way, there's another visual way to determine who's a maximum and a minimum in terms of increasing and decreasing. This one actually makes a lot of sense visually. You're a minimum if you transition from decreasing to increasing. You're going down, you're going up, you went through a minimum. You're a maximum if you transition from increasing to decreasing. You're going up, you're going down. When you transition, you're at a maximum. So you can identify maxima and minima relative to increasing and decreasing. But let's get back to the question. Where is there a relative maximum? In this context, where is an x question. This relative maximum occurs at x equals 3. What is the maximum value there? Again, as an adjective, maximum is describing the y value. The maximum y value there is y equals 9. Where is there a relative minimum? Again, where is asking at what x? This minimum is at x equals 0. What is the minimum value? That's asking the minimum y value, and at that point, y is also equal to 0. So it's really easy to answer maximum and minimum questions if you have a graph. For those of you heading towards calculus, you will learn techniques to answer maximum and minimum questions when you're given only a function, but not the function's graph. And no, the technique isn't draw the graph and then find them. It involves, well, calculus.